Good morning, you guys. I'm going to ask you to go into your Stoichiometry basics notes. These were delivered to you earlier in the course. I'm also going to post a link to these in the at the start of the module. So just in case you are gone, no worries, you'll have everything that you need. If you can scroll down to the section that focuses on mass in the mole, this is where we're going to pick up our learning for today. We've already talked a lot about atomic mass units and how the average atomic mass has been calculated. If that is something that you have not done yet or is something that you still have questions on, please refer back to the notes and the videos that are related in the upper portion of the module. All right, so I decided to pull just a handful of molar masses and just to explain a few things. One thing that you'll want to have out with you in this video is this document. So this is a table of atomic masses. This was distributed to you all before you left for our little break here. I also posted a link to this at the very top of the module alongside of the notes for this particular lesson. So make sure that you have that out in front of you. Take a screenshot of that, insert it into your notes. It's nice to just have it. This will be an essential piece that you will need, just like the periodic table, for the rest of chemistry. This is a document we refer to all the time from this point forward. So have that out in front of you at this time. All right, so if we're looking at, what does this mean? So if we're looking at that sheet and we can find out that the molar mass of copper is going to be 63.55 grams per mole. All of the molar masses that we'll work with, whether we're talking about a single element or a compound, we will round to the hundredths place. And the reason we're doing that is because at Esko High School, our electronic balances are only accurate to the hundredths place. We can never get something with accuracy to the thousandths or to the 10,000ths place. We just don't have the equipment to do that. So everything we're doing in chemistry right now is preparing you for work in the lab, and I want you guys to have your work that you're practicing on reflect what you would see or what you would have seen when you were conducting a lab here. So what does a 63.55 grams per mole even mean? A reminder to you that a mole is a unit in chemistry. 1 mole is the equivalent of 6.022 times 10 to the 23rd of anything that you're counting. Just like 1 dozen refers to 12 of anything, a mole refers to a really, really large quantity, which is very, very helpful in chemistry. If I had a mole of copper atoms, okay, so 6.022 times 10 to the 23rd atoms of copper, and I place that on an electronic balance, the electronic balance should read 63.55 grams or something really, really close to that. The same thing is going to be true of aluminum. If I were to place a mole of aluminum atoms onto a balance, so again, 6.022 times 10 to the 23rd atoms of aluminum, I should get a mass of 26.98 grams on that electronic balance. Now, some of you might be thinking, well, why, if I have the exact same number of atoms of each kind of element, why are they reading different masses? This will push you to go back to your understanding of density. If we were to look at the density of copper in comparison to aluminum, copper is a much more dense element by nature than aluminum is. So it should make sense that if we have the same number of each thing, that the copper sample will weigh more than the aluminum. Hopefully that makes sense. All right, so again, I just posted a couple of different kinds of elements. You can kind of look and just double check to make sure that you're understanding where that's coming from. Another thing that's important to remember is that some of our elements naturally exist as diatomic. So when you are reading a chemical reaction and it says something like, a sample of copper is reacted in the presence of oxygen gas and forms a copper oxide compound. We need to remember that when we're dealing with the oxygen gas, we're not just dealing with oxygen, which has an atomic mass of 16.00 grams per mole, but we're actually dealing with the diatomic version of that, right? There are 2 oxygen atoms that come together, share electrons for stability purposes. So when we're dealing with oxygen gas, we're actually looking at a molar mass of 32.00 grams per mole. Or if we're looking at hydrogen gas, it's 2.02 grams per mole. Or something like nitrogen gas, one of the most common things that we'll find in our atmosphere, 28.02 grams per mole. Now, I didn't fill out all of them. Again, this is something where you can step in and do the work on your notes if you choose so. If you're understanding it, I would just move on to the next concept. All right, finally, what we're doing here today is calculating out the molar mass of different compounds. So again, this chart is going to be really helpful for you as we're doing this. What I love about molar masses is it's something that has traditionally given students in chemistry some of their confidence back. I know we've done some really challenging things over the last couple of months that can shake your confidence or shake your abilities, but calculating out a molar mass tends to be something students enjoy doing and is something that they feel confident about, and it boosts their scores a little bit. So what you're going to do, and we'll start off with water, and what you're going to do is look at how many hydrogen atoms are in that compound. The subscript of hydrogen is 2, so we're going to put a 2 out in front, and then we're going to use the chart to find the molar mass. I'm not going to zoom back and forth. I've already pulled this information prior, but go ahead and reference your sheet. Pause the video as you need to so that you can calculate these alongside of me. So hydrogen, if we round that mass to the hundredths, is going to be 1.01. We're going to add that to how many oxygen atoms there is in water. So we have 1 times the molar mass of oxygen. Again, that's going to be 16.00. Then just plug that into your calculator. You do not have to do this mental math. You can if you want to, absolutely, but you can just plug that into your calculator. 18.02 grams of water for every 1 mole of water. What's great about that, you guys, is that water, which typically has a density of close to 1, if I had 18.02 milliliters of water in a graduated cylinder, or I had 18.02 grams of water in my graduated cylinder, that's 1 mole. So that's 6.022 times 10 to the 23rd molecules of water. So it's really easy for me to get a mole of water. It's not so easy for me to get a mole of marbles or a mole of pennies. I wish I had a mole of pennies. I would maybe not be making this YouTube video for you if I had that. But it's really cool because you can work with these really, really tiny objects, really, really tiny things, atoms, molecules, and very, very quickly amass moles of them. All right, let's do another one. Let's do nitrogen dioxide. This is, again, bringing in naming skills that you should have accumulated from earlier in the year. So nitrogen dioxide, nitrogen, and then the di representing 2, so this would be NO2. I'm going to do that exact same thing. I have 1 nitrogen, and nitrogen has a rounded mass of 14.01, and then I'm going to add that to my 2 oxygens, which each have a mass of 16, and then when I do that math quickly, I get a molar mass of 46.01 grams per mole. Always make sure that you're putting in that grams per mole unit for molar mass. All right, let's jump down to one that looks a little scarier, but again, if we just break it down into its little bits, it is not too scary. All right, so aluminum carbonate. All right, we have 2 aluminums. So we're just gonna break this down. Each aluminum has a molar mass of 29.98. All right, then if we look at our carbons, we actually have 3 carbons present there. Again, what you see here distributes to everything on the inside. So we have 3 times the molar mass of carbon, which is 12.01. And then we're gonna add that to our oxygen. Again, we have 9 oxygens, not 6, not 3. We have 9 oxygens, so 9 times 16.00. And when we plug that into our calculator and do all the math, if I've done it correctly, it should be 239.99 grams per mole. So if I had 6.022 times 10 to the 23rd compounds of aluminum carbonate, I would actually have a mass on the scale of 239.99 grams. One really quick thing, you'll notice I said molecule, and then I was like, oops, no. Molecule, that term, is reserved for elements that will share electrons. Aluminum and carbonate, those are both ions, so this would be an ionic compound. What I can do is just say compound instead of molecule or ionic compound. If I say compound, that will cover everything that we're working with in chemistry. So just a quick clarification there. All right, let's do one more. So sodium acetate will be my last example here. Again, you'll do a worksheet with practice on this. You will get the detailed answer key, and then you'll take a quiz on this. Take it a couple times if necessary. Ask questions, reach out if after you take those quizzes things just aren't seeming to add up for you. So sodium acetate, a reminder to you, this is where your periodic table is incredibly helpful. I have sodium, which has a plus charge. Acetate, those polyatomics that we memorized earlier in the year, or you can find them on the solubility rule sheet, which is also linked at the top of your module. So again, knowing the charge of each of those, then I can write the chemical formula for this. So the charge of sodium and the charge of acetate will cancel out. I'm just going to slide this over to make it look a little bit better. All right, now comes the work. So sodium, we have one of those. Sodium has a molar mass of 22.99. We're going to add that to carbon. There's 2 carbons, each with a molar mass of 12.01. I'm going to add that to the number of hydrogens times its molar mass plus the number of oxygens times its individual molar mass. Again, adding that up in my calculator because there is no way I am doing that math in my head. 82.04 grams per mole. All right, check out the homework assignment that is related to this concept. Hopefully it's a really straightforward, simple thing, but again, if you have questions, reach out. Do not hesitate to ask.